Hello. Hello, can you hear me?
Yes, sir.
Yeah. Okay, good. So, any questions about whatever has been done so far in the class? Hello, can you hear me?
Yes, sir.
Okay, good. Okay, so any questions about the problem set that has been given and so on? So I forgot to post. There is an assignment that has been already been made. I will post it today, tonight rather. It will be on the dynamic programming mostly. But yeah. So, any questions before I start with today's lecture? Excellent. So, if you don't have any questions, I will just jump into today's lecture. And today we will be doing a kind of a new topic as rather. I will be moving from whatever we were doing till now to a new topic. It is also in algorithms in the sense that it is some kind of an algorithm, but they are more for graph algorithm. So here is the problem that we will be focusing on. Okay, so this is a problem written not in terms of a graph or something, but as a problem that has been problem in real life kind of stuff. So there is an internet provider who have to lay fiber cable, and the job is to connect cities, right, using the cables. And the goal is basically to minimize the cost of laying the cables, yet ensuring that everybody is connected by the cable. Now, this is a problem that you can imagine has been solved regularly over the years, maybe for laying down, sorry. Yeah. So for laying down electricity connections or various kind of coming up with different routes and all to ensure that people are getting connected what is the quickest way of reaching people who are kind of say after a cyclone and all, there are roads and all are broken. What is the minimum amount of road or cost of road that can be fixed so that everybody is somehow connected? So this problem has been there again and again and again, and it's something that that's always an important problem that's there. So any idea about how we can go about trying to solve this problem? Let's see. Shomukanti Shaha, are you there? Hello. Shomukanti Shaha, are you there? It seems like he is not there. Okay. Subir Das, are you there?
Yes, sir, I'm thinking.
Yes. Any idea how can we go about this problem? Okay. Mayank Deora?
Yes, sir.
Yeah, do you have any idea how to go about this problem?
Sir, we can use greedy approach for solving.
For having which
The
one?
minimum spanning.
Good. So somebody has pointed out this one. So again, this is something that is important here, that whenever you are asked to solve a problem like this, okay, one natural thing to do is to think about representing it in one of those forms that you have kind of possibly seen in some sense. Okay, so the first thing to do is that convert this problem into a well-known form. So standard well-known form, whenever there are such kind of things like connectivity, cities, and so on and so forth, it is natural to think of it as vertices and edges in a graph. So of course, we know what are edges and what is a graph, and I don't want to go into this, what's the definition of vertices and edges and all. And imagine, remember this one. So this is an example which has been done in your discrete math course and even in the algorithms course, that many times this graph theory, a graph helps to kind of write a problem in an abstract way, okay, into a same kind of structure. And this is why we study graphs or graph algorithms in particular. Okay. And so here, for example, what we can do is that we can use the cities as vertices, and we have these roads that connects the cities, and each road comes up with has some distances associated with that. Okay, or you can think of it as the cost of laying a fiber network along this road. Okay, and what is the thing that we want? We somehow want to select a few set of roads such that every vertices is connected, right? And we want to minimize the sum of the set of roads selected. So maybe let me ask you again if I can find out some people. Soumyakanti Saha, are you still there or not there? Soumyakanti Saha?
Hello, sir.
Yeah.
So, yes, sir.
I mean, I had called you earlier once. You did not
Oh,
answer.
maybe the internet connection is not good here, so that's why there is a problem.
Okay.
I think.
So can you tell me, I mean, if I have given you a graph and I want to connect the graph, what is the minimum number of edges that I need to connect to keep the graph connected?
N-1.
Okay, and what is the kind of structure that helps me to keep the graph connected?
Linear structure than that.
Linear structure. What is a linear structure?
I mean, if I join the NH by N-1,
No, but that you have not allowed. You have a certain set of edges and you have to choose only from those set of edges.
So can you please repeat the question again? Then?
You have been given a graph,
yeah,
on n vertices. How many edges do I need to select to keep the vertices, the graph connected? Okay. You are not allowed to draw new edges. You can only use the previous edges. Do you, hello, are you there?
by tree structure can be.
Okay, it's a tree structure. Good. Good. So basically, we have to come and produce a tree structure, right? And this is what we have to do. Okay. So what we want, so this is it, that we want to keep all the cities connected, and we minimize the total cables cost. So minimize the sum of the weights of the selected edges. And again, so in the case of an undirected graph, right? Okay, we know what is the concept of a connected graph. So note that if the original graph is not connected, then there is no question of connecting them, right? So that is no question of that. So we have starting with the connected graph, okay, and we have to come up with a tree, because it is natural that a tree is the minimal structure that connects everything. So our job is to find a tree, a subtree, right? And basically there are lots of definitions of trees. So a tree is a graph that is minimally connected. A tree is a connected graph that has no cycles. So these are the two standard definitions or equivalent definitions of a tree, right? And we will be using this definition. There are other definitions also. So okay, there is another definition that tree is a connected graph. Sorry.
Sir, if we say that this is minimally connected, then there is no point to say that G has no cycle.
Exactly, they're all same. Completely right.
Yes.
So all of them are, three of them are equivalent definition. Okay. So if a graph is connected and minimally connected, then the graph doesn't have a cycle. If a graph is connected and has no cycle, then it is minimally connected. If a graph is connected and has n-1 edges, then it is also minimally connected. It's also it has no cycle. So these three definitions are equivalent of each other. Okay, I'm not saying that they are different. I mean, they're describing some other objects, or we need all the three things. I'm saying is that I'm just saying this the properties of a tree. All the three definitions are equivalent, right? And a spanning tree is that given you a graph, a spanning tree is a tree that touches. I mean, I give you a connected graph G. A spanning tree is a tree that touches all the vertices. Okay. And yeah, so that's fine. And we want to minimize the cost of the amount of cost of laying cable. What does it mean by that? That if I look at, so I want to select a set of edges, right, in the graph, such that every vertex is connected. So of course, I want to connect them minimally. I don't want to spend too much extra cost, right? Which means that I want to select a spanning tree. And once I select the spanning tree, I want to look at the cost of laying cables along the spanning tree. What does it mean? I want to look at the sum of the cost of the edges in that tree. Okay. So a tree with the minimum total weights of edges is called a minimum spanning tree. Okay. Is this definition clear? The minimum spanning tree?
No, sir. Can you please repeat again?
Sorry, who are?
Somogan.
Okay. So which part did not you understand?
I mean this weighted definition, that minimum spanning.
Okay. So if I give you a tree, okay, a spanning tree, okay, there can be many spanning trees in a graph, right? I can have
Yes.
this spanning tree 1, spanning tree 2, spanning tree 3, and so on. Now, for any spanning tree, the cost of associated to the tree is the sum of the weights of the edges in that spanning tree. Is this clear? What is the cost of a spanning tree?
Okay. Okay. It's okay now.
Is it clear now?
Ah,
So
yes, sir.
minimum spanning tree is the minimum over all the spanning trees, which has the minimum cost. Is it clear?
Yes, sir.
Okay. If it is clear, yeah, I will like to go over this example once actually. So here is a graph, the weighted graph. So this is a spanning tree. Okay, the red edges is a spanning tree. And what is the cost of the spanning tree? If you look at the sum of the edges, weights of the edges in the spanning tree, you will see that the spanning tree sum is 54. So this spanning tree has cost 54 or weight 54. Okay. Now, is this a minimum spanning tree? It turns out that there is another spanning tree. This is also another spanning tree. The red edges also now represent another spanning tree. So both of them are spanning tree. This is a spanning tree and this is a spanning tree. But this one actually has weight 45. Do you think this is a minimum spanning tree? So this
Till now, sir.
Sorry?
Till now, this is the minimum.
I mean, among these two, this is the minimum. But in
Yes,
this
that's
graph, is this the minimum spanning tree? In this graph, is this the
No,
minimum
sir.
spanning tree?
No, sir.
No, sir.
11 GF can be replaced by DF6.
which one? C and
Yes.
G can be replaced with D and F, right? Excellent.
Yes.
Because what is happening here? See, this is something very crucial over here. Okay. So what you guys told is very interesting. What is another property of a tree? Another property of a tree is that if I add an edge to a tree produces an unique cycle. All of you fine with this?
Yes, sir.
Excellent. So I can just take any edge. So say it might be D of E, DE this edge, or DB or BE, it doesn't matter. I can take any edge and I can add this one, add that edge to this graph. So it creates a cycle, right? So maybe I can use my board here. Hello, can you see something? Okay, maybe I will just talk about it. Issue with the connectors. Wow. Okay, so anyways, so just one second, maybe I can do something here. Just one second. Okay, while I try to connect my iPad to this one, I can keep on. Okay, I got it. Just a second. Hello. Can you see my screen?
No, sir. It's still see screen sharing is happening.
Something weird is happening. Look screen. Bizarre stuff are happening, and I can imagine that you are unable to see it still now, right?
Yes,
sir. Says that you're screening, screen sharing, but we can't see anything.
Hmm.
I have no idea what's happening here.
Showing the other user, what that means? Okay, I have no clue what's happening. Recording. This is bizarre. Okay, forget it. I think I have to go back to our whatever I have. So anyway, so basically the problem is that if I join, say if I add this age df, then what will happen is that I will get a, so if I add an age like df, then I will produce a cycle, a unique cycle, right? The cycle will be the whole thing, a d a b c e a, g f and d. Good. So now in a cycle, I can remove any one age, then still the graph will remain connected, right? So the idea is that if I can therefore add an edge of a smaller weight and remove an edge from the cycle of a bigger weight, then I'm in a good shape, right? Then I will be able to reduce the weight of the spanning tree. And this is exactly what happens. If I add this DFA of weight 6, and then I can go around and say, oh, see, there exists an edge. I mean, there's an edge with the B to C. I can remove that B to C edge, and I will actually reduce the edge. Or I can remove this F to G, and again, it will reduce the edge, reduce the weight. So this is what happens. And if you see, if you do this whole thing, you can actually, for example, here some of you told that add B to F, but then there is something else. Like I could have added B to C edge. If I added B to C edge, then the cycle that would have been formed is BCE. And in that case, B to C is weight 7 and B to C is weight 8. So I can add this edge BE and remove BC, and again, I will have still produced a minimum edge weight. So such in using this trick, you can see that you can slowly get to the spanning tree. The minimum spanning tree actually here is of size 39. Right? And this is the kind of very important, crucial aspect of the about this spanning tree that we will be using. Good. So the goal, what is the goal? So the algorithm that we have to find out is given a graph and its weight, we want to find the minimum spanning tree. Now, how can we come up with an algorithm for this? Now, there are actually quite a few algorithms from this direction. Okay, how to find out the minimum spanning tree. And some of them are easier than the others, or I mean, they are different style than the others. Rather. So in this particular class, we will be presenting a very greedy algorithm. So by the way, till now, I mean, we have seen examples of these three kind of algorithms: divide and conquer algorithm, like the merge sort; dynamic programming algorithm, where we divide and conquer, but the idea is that we store the data to be reused again, and that is called basically dynamic programming, right? And then finally we have the greedy algorithm. So we have seen greedy algorithms earlier also. For example, the bubble sort and so on are greedy algorithms. So it is natural that we will so greedy algorithms are very natural algorithms to try, because they seem to be like, oh yeah, they are obvious, we should go about trying to do this one. But at the end of the day, what we realize is that while greedy algorithms are natural algorithms, proving them can be a bit tricky. That the fact that this algorithm actually gives the correct answer is a bit tricky. So here is a very greedy algorithm that we'll present. Okay, so the main idea is to kind of greedily solve the problem and prove that the output is actually right. Okay. So to start with, here, let me go back here. Let me go here. So if I tell you that this is the graph, can you tell me one particular edge that will certainly be present in but that will be present in a MST? AD. Why?
Because this edge is having the most smallest weight among all the weights present.
Correct.
Even EC is also possible.
Yes, so since it has the smallest edge weight, right? So if somebody comes up and says that, oh, here is a different MST, I can, which doesn't use say AD. What I can do is that I can just add the AD. Again, if I add the AD, it will produce a unique cycle. And now I can remove any edge from that cycle to get another spanning tree. But since AD is minimum among all the edge weights, so whatever edge that I will remove from that cycle has to have edge weight greater than or equal to 5, right? Which means that give me any MST, I can produce you another MST that will have the edge weight A2. This edge A2. Is this clear?
Yes, sir.
So this is a very crucial thing. So that means, see, I'm not saying that actually any MST will contain this minimum edge weight. What I'm saying is that there exists a MST that contains the minimum edge weight, the edge with the minimum. Because see here there can be two edge weights of length 5, right? Of weight 5. I cannot say that both of them will be there, but at least one of them will be there. Or in fact, if you choose any one of them, I can always produce an MST that contains that particular thing. Okay. So the first and most natural thing to do when you start creating a greedy algorithm is that, see, I have found out that there exists an MST which contains the minimum edge. So why don't I start by picking up the minimum edge? That's the most simple idea to do. Okay. And that is exactly what we will do. We will pick the minimum edge, minimum weight edge. What will we do the next thing? The next thing is that, again, by the same kind of a logic, if there exists another minimum, if there is another edge of minimum weight, I will pick that edge. If possible. What does mean by if possible?
We will check that whether on adding this edge in our MST, we are getting a cycle or not.
Exactly. Because it might be that the first edge is not a problem. But maybe when I take the third edge or something, fourth minimum edge, I might be producing a cycle. And our job is not to produce a cycle, right? Our job is to produce an acyclic graph. So that's why we should always ensure that the edge that we pick up, we should ensure that the edge that we pick up doesn't produce a cycle. Okay, so you can say, how is it possible? So imagine that graph has all the edge weights are same. All the edge weights are same. So every edge is a minimum weight. So you of course pick the first any of the minimum edge weight, any edge rather. Then the next one you pick another edge. Then you take another edge, but that edge might produce the cycle, right? So it is possible that this edges, minimum edges, produces a cycle. So we should check for that. Okay, so this is what is called the Kruskal's algorithm. It's a very, very greedy algorithm. So the main idea is that you start by picking up an minimum edge. So I start with say picking up with AD. Among the set of other edges, okay, what is the next minimum? Is EC. Okay, good. So let me pick up the EC. What is the next minimum among all of these things? Okay, it's DF. Excellent. I will take DF. What is the minimum, next minimum that I should pick? Okay, maybe AB. So that's 7, right? What is the next one? Okay, BE. Okay, I pick this one. B. Now at this point, what is the next minimum? The next minimum is actually B and C, but that is 8. But if I pick that edge, then I will produce a cycle. So I should not pick it. I should throw it rather. And instead, I should pick an edge which is the next minimum after that. Okay, the next minimum, the next edge can be DB. DB is 9. But again, if I pick this edge, then, oh, sorry, not DB, it will be EF, right? Again, if I pick this edge, I will produce a cycle. So, okay, I need to throw them away again, because that's not good. The next one is the DB. Again, I pick this one, it produces a cycle. Not good. I throw them away. Again, I will pick this EG, right? And when I do that, then I will check that EC, I will check BC, I will check DB, and finally I will check EG, and that is it. Okay, so this is basically the Kruskal's algorithm. Why does it give you the correct answer? Let me come to that later on. But okay, we go over all the edges, and so here is the pseudocode of the algorithm. So what is it? So we have been given the graph. We start by sorting the edges in an ascending order of the weights. And okay, basically what we do is that, okay, forget whatever is written here. Yeah. Yeah, so forget all of this. So basically what I want to do is the following, okay? I want to pick an edge and the ascending order. Then I want to see if that edge produces a cycle or not. And if it does produces a cycle, then I will not take it. And if it doesn't produce a cycle, I will keep it. Is this algorithm clear? Hello.
Yes, sir. Yes, sir.
Good. Now, can you say, I have not yet written the pseudocode of the algorithm as such. What is the running time of this algorithm? Manisha Panda, are you there?
Yes, sir.
Yeah, can you help me to find out the running time of this algorithm?
Order of number of edges.
Order number of edges, that's it. So first thing, what should we do? Actually, you start with
Minimum age.
I should find the minimum age. Okay, so every time I find a minimum age, how much time does it take to find a minimum age?
So is it ordered n square?
Just 1 second.
Is it will take order of order of number of ages.
Okay, so first age to find out, it take order number of ages. Okay, good. What will it take the second time? How many times? How
Same.
much time does it take to find out the next smallest age?
It will also take order of number of ages.
It will also take order of a number of ages. So if I keep on taking the order of number of ages number of times to find out the next smallest and so on, how much time does it take all total?
E square it will take.
Oh, the e square. So not the order of e, right?
Yes, sir.
Okay, can you improve this particular thing? If I have to just, if you have to, all you have to do is keep on producing the first produce the smallest stage, second produce the next smallest stage, third produce the smallest stage after that, and so on. How much time will it take for you to do output the whole thing? Hello?
Yes, sir.
Yeah. How much time will it take for you to output the whole thing? Is the problem clear?
Yes, sir.
Of
So
course,
it
you are telling
is
me an order e square time. Like first one take order e, second one takes the order maybe e minus 1, third time take e minus 2, and so on. It is order e square number of edges. Time. Can you
Yes.
do better?
For now, I can think of anything.
You cannot think of anything. You think a little bit more, because this is something very trivial. This is something that we have done in the beginning of the code.
So if we
Okay, we
sort
can.
the areas according to the weight,
Exactly. If you sort the edges according to the weight, the total time taken for sorting is order e log e. And then we have the sorted edges. Manisha, was this very hard?
Yes, sir. No, sir. Yes, you can do that.
Sorry.
Yes, you can sort, then it will be, time complexity will reduce.
Yeah. Okay. So that is the first part. If you want to, you can sort, and then every time you can produce the next minimum one with in order one time after that. So you have order E log E to initially sort it. But then what? Let's see. Mayank Deora?
Yes, sir.
Yeah. Say I have sorted the number of edges. After that, what happens? How much time will it take for me to for this whole algorithm to run?
Sir, we will one by one pick the pick the smallest edge and check whether it forms a cycle or not.
Yes. So how much time does it take?
So for detecting the cycle, we can. Sir, I exactly don't know, but we can use set the set finding of find
Okay,
set
how
of.
much? If you don't know means what? You cannot give me any algorithm that will help me to find a find whether there exists a cycle. Do you know of any algorithm that will help me to check whether a cycle exists in a graph or in a subgraph?
We can use BFS, but here we have to see that whether a node has been already visited or not. If it has been visited, then there is a cycle on picking the new edge. So if we are selecting an edge, then we have to make a save the nodes also of that edge. Like if we pick AB, then we have to store A and B also. And if we again pick an edge like BD, no. Sorry, I don't know exactly how to do it.
I mean, you don't know any algorithm how to do it. You told the BFS, DFS, and something, right? How much time the BFS and DFS take?
BFS takes order of V plus E.
Okay, so if I use BFS, then how much time will it take all total?
Then yes, sir. Then it will take big of E log E. I mean, the sorting complexity will be dominating.
Sorting will be E log E, and
then V plus O V plus E.
it's V plus E only. Rupsha Mitra, are you there?
Yes, sir.
Do you agree with what Mayank told? After we have sorted the total amount of time that will take is order V plus E.
Like finding a like loop in this graph.
Finding a loop will take order V plus E. What is the total complexity of this algorithm?
Okay, then it will be. Yes, sir. I kind of agreed with him. Like E log E plus V plus E.
So after you take the first edge, okay, you said take the second edge. How much time will it take to check whether there exists an edge or cycle or not?
That is DFS. We can by DFS we can check it is there is a loop or not.
Yes. How much time will it take?
Okay.
How much time will it take? Just tell me.
At most n, like order of n, where n is the like maximum of V or E.
Okay, fine. Let's say the maximum of V or E is n. Okay.
Hmm.
Fine. You take order n. Now you take, say you choose that edge. Okay. Now take the third edge. If you want to add that edge, you want to check again whether there is a loop or not. How much time will it take?
Okay, order of n minus 1.
Let's say order of n minus 1. There's a fourth edge. How much time will it take?
Okay, I got then n up to 1. So it will be like n square order of.
It will be a n square, right?
Yeah.
Order of E square. All total. Mayank, did you follow?
Yes, sir.
No or yes?
Yes, sir.
So every round will take order log E log order of V plus E. Okay. But to complete the whole thing, we have to go for all possible edges, one after another, right? And every time you have to solve this, whether there exists an edge, whether there is a cycle there or not. So all total, it will take order of E log E for DFS on each round, and it will be ordered E rounds. So it will be order of E square algorithm. Is this clear? So if you are using BFS or DFS to check whether there exists a cycle or not in this graph that we have chosen, then it will take all total order of E square time. Is this clear? Hello?
Yes, sir.
Yes, sir.
Okay, good. Now, can anybody of you think of a slightly better algorithm? Do I need to really spend almost so much time to check whether a cycle will be formed or not? Do I need to really go into this whole DFS and DFS business?
By adding an edge, just check whether we are producing a new vertex or not.
Okay, if it produces a new vertex, then certainly we know that it cannot be a cycle. Very good.
Yeah.
But whatever they both are, none of them are new vertex, then?
So like whenever we are choosing an edge from our sorted list of edges, we can check that both whether like both of its endpoints are already visited or not. If that's the case, then it will certainly create a cycle.
It will it?
It will certainly create a
Okay,
cycle.
let me
Like
think
if
of it.
both
Okay,
of
so
it-
here at this point, I have picked up these three edges. I mean, these three edges, right? So D,
Yes.
B, C, D, A, B, D, and F has been visited. I've also picked up this edge, E and C.
Yes.
So now, if I pick this edge, B and C, both the edges are there, right?
Oh, yes.
So that so I agree that if you have both the edges are not visible, both the vertices are not visited, then you cannot produce a cycle. But if both of them are visited, then I cannot say that it will certainly produce a cycle.
Oh, yes, sir.
Then what?
And we need to maintain an array visited, that we will mark if that is included in the shortest path or not.
Shortest path?
I mean, spanning tree.
No, exactly here. So there is an array, right? One array says that, I mean, the set of edges visited or vertices visited is A, B, C, D, E, and F. But now I pick this edge, B and E, B and D.
Yes, and then we will mark P and D as 1. And I mean, visited of P and equals to 1 and visited of E equals to 1.
Sorry, can you just repeat once again?
We will maintain an array, I mean, where the vertices are numbered from suppose 0 to n minus 1.
Fine.
And suppose B is visited of B when edge A and B is included, then visited of A is equals to 1 and visited of B equals to 1. This we can keep.
Okay, good. So basically, what you are saying is this following. If you guys have not seen it, you can see that the reason these two things are colored green and these four are colored red is for a reason. This is something similar to what I think Ujjal was saying, I think. So when will you create a cycle? You will create, see, these red things, red vertices are a connected component. These green things are another connected component. If I take an edge, say like D and B, both of which are in the same connected component, then I will produce a cycle. If I take an edge that are across two connected components, then I will not produce a cycle. So I need to keep track of which connected cycles, connected component each belong. Okay. So how I do it? Let me go back and do it. Show it to you again. So I first take A and B. Okay. I just make one of them to be its minimum, to be its representative. Say A is the representative. So how I do it? So in D, I will say that okay, D has a representative and that is A. A has a representative, that is A itself. The next one I take E and C. Again here, I say that okay, see, E doesn't have a representative earlier, C doesn't have a representative earlier. Now that I have chosen this one, I take the representative of E and C is C. Say. So representative of E is C, representative of C is C. Now I take the next edge, which is the edge DF. So what should I do now? See, I have added this new edge. In this edge, one of them has been already been looked into, right? The other one has not been looked into. Since this has been already been looked into, so this representative is stored. This representative is what? A. And so I said, oh, F's representative is same as the D's representative. It is A. So basically, these three vertices, all three of them representative is the representative of the whole connected component. It is A. The next, I do the same thing for B. Now, oh, see, now I have got this one, and B's representative is same as A's representative, and that is A. So again, all the four now has a representative which is A. All these two has a representative C. Now I come to here. I looked at this BE. Now when I look at this BE edge, I realize that see, it is connecting two vertices. Both of them has been previously been seen, but the representative of these two things are different, which means that they belong to two different components. So I can add them. But once I add them, I will need to change the representatives of E and C also. And this is what I will have to do. I have to go and just say I will change the representative of E and C. And so now everything will be updated to representative of E. So every vertex in this connected component has representative A. And now we look at some other edges. So like this edge, if I look at this EF, then this edge is connecting two vertices, both of whose representatives are same. And therefore, I know that these two are from the same connected component. And hence, I should not be picking up. But if I pick it up, then I will produce a cycle. Similarly, B and C. And similarly, D and B. And now, if I look at this last one, E and G, I realize that one is not even visited, and E has been a representative A. So I will just add. So this is the trick that is there. So to maintain this whole thing, all you have to do is then maintain the representative. Okay, and this is what is done in this pseudocode. Okay, so you first sort the edges in an ascending order. Now for every edge in the order according to the ascending order, if the so initially representative of every vertex is itself. So if the representative of a particular vertex is not same as the representative of the other vertex, then I will add this edge UV to this set, and I will update the representative of S and representative of U V as representative of this union of them. So I am not representing that connected component as two as any particular element. I'm representing the whole connected component as the union of the elements. Now I will let you guys think about how much is the turning time of this algorithm. Okay, it's a bit of a nice interplay that you have to put in, because there is some kind of a data structure in play here. But the main idea is simple, that instead of every time I add an edge, instead of going and searching or doing a DFS or BFS to find out if there exists a cycle or not, or if a cycle is produced or not. All I need to just keep tag of is if these two vertices, or which connected component does any particular vertex belong. If two vertices belong to the same connected component, then the edge connecting them will certainly form a cycle. If they come from two different connected components, then they will not form a cycle. And this is all that you have to kind of keep in mind. Okay. Now, okay.
Sir, can you go back?
Yeah.
Just give me a minute.
Are you copying this whole thing?
No. I was just checking it. Like when you were saying, I was just listening to it. I just
Okay.
wanted to have a look. Just 2 seconds.
Sure. So one thing to kind of observe here is that this graph will certainly produce you a spanning tree. Okay, that is kind of clear. If it is not clear, then you can try to prove it for yourself once and for all, that why will this give you a spanning tree. So basically, if it is not a spanning tree, then some vertex has been left out, then there is an edge coming out from that vertex, right? Why was, when that particular edge was being looked into, why was it not selected? How is it possible that that is not selected? Because that edge, adding that edge would not have created any cycle. So that would have been connecting a isolated vertex with another thing. So that means it should have been selected. So by that argument, you can very well see that what comes out is that the graph. The graph is a spanning tree. In fact, you have to prove that the graph is connected also. Okay, so you have to prove the three things about the connectedness. It is not, none of them are actually obvious. First of all, that the graph is connected, the graph has no cycle, and the graph is a spanning tree. Okay. Now, why the graph connected? Again, I think this is something which I just now discussed. Okay. Yeah. So look at this. Any kind of this. Take any connected component. Basically, this SV, which is basically the kind of representative of the connected component that contains V. So that is connected, right? And you can prove that at the end, every vertex will have to have produced in the same set. Now, I am kind of going to skip this proof here. I let you guys go and think about it. That how to prove formally that the graph is connected at the end. Okay, it's a more the fact that we'll never have a cycle. This is kind of more obvious because we are ensuring that every time you are picking up an edge, no cycle is being formed. So that cannot happen. The more interesting part to prove is that why is this an MST? And this is where I think the property, not I think, that this is a place where whatever we were discussing in the beginning actually helps. Particularly here, I mean, I have kind of written it here properly, formally, that if we add an edge to a tree, a cycle is formed. That's important. If you remove any edge from the cycle, we get back a tree. And yeah, so this is basically follows from this fact, right? So say T be the output of the Kruskal's algorithm. And let's say that T mean is an MST. What do I have to prove? I don't have to prove that T is equals to T mean. No, that I don't have to prove. I have to prove that T and T mean has the same weight. right? Now say I ordered the edges. Say the edge E, say UV is the smallest edge in the T mean that is not in T. Okay, that is smallest edge that is in T mean that is not in T. Right? So say that E is the kth smallest edge in T mean. Okay, so that means there are these edges beforehand, all of them, right? So therefore, you find that this edge E0, which is the kth edge in the T, so that has some, that is say E0. So what we know, right? Yeah. Actually, I think what is written here is a bit of I made some lot of mistakes over here. So I think I will just keep here. I will just keep here and I will let you guys go back and try to prove it. Okay. So the main idea is that you take the T that is coming from the Kruskal's algorithm and take any T mean that is the minimum spanning tree, right? Look at the, so, and you order the set of edges. Okay. You order the set of edges. So the first k edges of both T and T mean are same, identically same. Right? The next one, now if I could have written, which I cannot unfortunately today, it would have been sad that I cannot write it. Let me just try to see if I can do it again. Okay, so for some reason this is not coming out, and I don't know why. So anyway, so let me try to explain in whatever in the word as much as I can. So I have these two things, right? There are the T1 to T. Right. So I have this tree T that is coming from the Kruskal's algorithm, and the tree T mean that is say one of the minimum spanning tree, right? Then say the first k of the edges of T is same as the is present in T mean. So the edges E1 to Ek is present in T and in T mean. Now consider the first one, which is not there, right? So edge Ek minus Ek plus 1 is an edge that is in T, but that is not in T mean.
Sir, are you sharing anything?
No, I'm not sharing anything.
Like, okay.
I'm not sharing anything, and I don't know how to. I don't understand why is this thing not allowing me to share over here. Can you see something now?
Yes, sir. Whiteboard.
Whiteboard.
Good enough for me for now. Okay, so say I have this T That is what I have got from the Kruskal's algorithm. And at the T mean that I have got, that is the some MST. Now my job is to, what do I have to prove? To show that the weight of T is equals to weight of T mean. Okay, so this is actually a proof by induction to some level, but let me just explain the idea. So I can write this T and I write it as the set of edges E1. So basically I'm writing this E2 till En minus 1, right? But this less than basically means that weight of E1 is less than weight of E2 is less than E3 and so on, right? So the K, and what is T mean? So T mean contains say E1, it contains E2, it contains EK, but here it doesn't contain EK plus 1. It contains the EK plus 1 bar and something else. So this is the first place where T and T mean differ. Okay, I'm not saying that this edges here. So first of all, note that whatever edges here, it cannot be, so it is not possible that I have a edge here which is actually equal to the first edge here or something like that. That is not possible, right? Or it cannot be the following, that it is not possible that this edge is much later on. Can it be? Do you think it is possible that this edge is much so also I'm kind of, this is also I'm doing it. Okay. Is it possible that this edge is much later on? Hello. Hello.
No, sir, because our algorithm is choosing minimum edges, right? Every time, minimum.
Exactly. Since it's taking minimum edges, so if this one, if this edge, this vertex, this edge appears much later on, what does it mean? That means this edge is smaller than this edge. Can that happen? Can this vertex is smaller than this edge? If it is so, then in T, I must have looked at this edge and discarded it. Why did I discard it?
Because it might have formed a cycle.
It has formed a cycle. So that means I have E1 to EK and this edge that would have formed a cycle. So this is not possible. So it must be the case that, so this cannot be the case. So it is not that EK plus 1 appears later on. That is not possible. Okay. Fine. So therefore, we know that EK plus 1 must be lesser than or equal to EK plus 1 bar. Right? I know that. In fact, everything here is all of them are bigger than or equal to EK plus 1 bar. Correct? Good. Now, what can we do? Now, what I can do is that I can add, consider this one. So I have this T mean and I add the edge EK plus 1. So therefore, so I add this edge. So what happens there? I will produce a cycle in that new, in this graph. So I should remove some edges. So in this, so this is T mean. Let's say this is T mean, kind of some kind of a structure like this, and I have added this edge. Now once I add this edge, I must remove some edge. Note that if I, since I've added this edge, I should, and it doesn't make a cycle with the previous ones, right? That's what is guaranteed by T. It must be producing a cycle with the later ones. So I should be removing an edge E T where T is bigger than k plus 1. So somewhere here, maybe the ET is somewhere sitting here, right? So this is another spanning tree, correct? I have taken the T mean, the minimum weight spanning tree. I have added the EK plus 1, right? And that produces a cycle. Then cycle must include some edges from on this side, on the left side of sorry, on the right side of EK plus 1, and I should remove that, and that produces me another spanning tree. But what is the weight of this spanning tree? What is the weight of this spanning tree?
Lesser than T mean.
This is minus EK minus plus 1, sorry, plus minus ET. But since I know that this one, EK plus 1 is lesser than EK plus 1, this is of course lesser than or equal to ET. So I have added something lower and removed something bigger. So this must be lesser than or equal to T mean. But I also know that since T mean is the minimum, the weight of the any spanning tree must be bigger than T mean. Weight of T mean. So that means this graph is another minimum spanning tree. Is this idea clear? So if the spanning tree obtained by Kruskal's algorithm is not same as the spanning tree obtained by is not equal to the another spanning tree, then I can produce from T mean, sorry, I will produce from T mean, I will produce another T mean prime, which has the same weight, of course, because it's a minimum spanning tree, but it now has what? I have replaced EK plus 1 with EK plus 1 bar with EK plus 1. That means now this spanning tree and this spanning tree matches in not K plus 4 K edges, first K edges, but it matches in K plus 1 edges. Is this clear?
Yes, sir.
Should I repeat it again?
I mean, it's clear to me. Yeah.
Okay. So I started with the T mean that matches with the K edges, first K edges, then it produced you another MST that matches with K plus 1 edges. So by repeating this whole process, by induction, you can prove that the weight of T is exactly equal to weight of the minimum spanning tree. Because the next thing that you do is that you produce another spanning tree, minimum spanning tree, which matches on with T on K plus 2 edges. And then we produce another spanning tree which matches with T on K plus 3 edges, and so on and so forth. Till you find out that okay, here is the minimum spanning tree that matches with T on N minus 1 edges, which means that it is a spanning, that means T is a minimum spanning tree. So that is basically the main idea of the minimum spanning tree. Is this clear?
Yes.
Okay, perfect. I mean, so again, if you have not got it, it is not hard. It's a bit of this old graph theory kind of argument. Minimum spanning tree for Kruskal's algorithm is there in almost every book. So I would request you to go and take a look at that proof. Okay, this is something that is used a lot. I told you that proving the correctness of greedy algorithms is slightly complicated, always, because you do something greedy, And then the idea is that why does it output the correct answer? That's a natural question to ask. Okay, and that's what happens. Okay. So now let me complete this thing. So what is the time taken? Now, okay, to sort the edge, it takes order E log E number of steps, and the rest will take order E steps. This is a part that I have not yet completely given you the right idea. So you guys try to go and fix it, because see, if you just use the DFS or BFS every time to find out a cycle, you will, what you will get is order E square. But by somehow maintaining this this representative kind of stuff for every connected component, you can actually improve the time significantly. So the total runtime will become order E log E. I am not yet telling you the whole thing, because there are certain data structure issues that will come in the picture. So I don't want to go into the data structure issue. So I will ask you to go and read this one thing from this algorithm from any book, whatever book you are comfortable with. The two things to remember is that first of all, this is an algorithm where there is a lot of nice implementation issues that you can do. It's a greedy algorithm that has some nice implementation stuff. For example, if you don't sort the algorithm to start with, then you take order E square steps, and so on and so forth. And the other issue is, of course, that if you don't, at the end of the day, if you you have to prove, because it's a greedy algorithm, that whatever is the output is actually correct. And proving this one is slightly more complicated than the standard recursive algorithm. Okay, so I think I will stop here unless you guys have any questions about. Yeah,
can you go to the algorithm one, sir?
I can go to the algorithm once again.
Like the pseudocode for this one.
Yeah.
Oh, yeah, this one. So I'm having doubt in this step. Sir. If SU is not equal to SV, like it's, you know, imagining that is kind of hard. Can you just explain that one part? So what we are doing is, first we are taking every vertex in V. Hello.
Yeah, yeah.
And then we are taking every vertex and we are forming a set which is SV. And then we sorted the edges. That's there. So for when this means that, you know, U comma V is an edge, what does it mean SU is not equal to SV?
So here what it means that the set SU is not equal to set SU. Okay, so basic idea is that the set of connected components, set of the all vertices that is connected to U is not equal to the set of connected vertices that is connected to V. Okay, so if you actually have found out some problem in the pseudocode, then you are great, because actually pseudocode has some problem. But that is because this representation of the representative has not been done correctly. So I will let you guys go and then really try to think about it. Okay, what is it that you can do? So this is,
I mean,
you have to use
like,
some kind of a data structure, but the basic idea is that you want to keep for every vertex the representative of or the set of all vertices that is connected to that vertex, or a representative name, basically. Okay. At any point of time, all the vertices in a particular connected component should have the same name or same representative. How to do it is something that I'm not exactly telling you.
Sir, like, no, here, so for example, let's take this one. SU is basically just U, right?
To start with,
Yeah, for the starting point, SU is just U and SV is just V.
right?
So given U is not equal to V, we add this to the set A.
Right.
After that, what does the SU become?
So SU becomes SU U union U comma V, and V becomes V comma U comma V. See, SU, think of SU to be the set of all vertices that are in the connected component of U at any point of time. Okay. So for example, here,
yeah,
at this time, SB is ABDF, SD is ABDF, SF is ABDF, SA is ABDF, S of E is E and C, S of C is E and C, and S of G is G. Now, when I get this edge, B to E, what do? I will connect them. So now I have to update the S of everything accordingly. So S of B will become whatever was there, A, B, D, F, union E, C. So S of B, therefore, if I add this one, S of B will become A, B, C, D, E, F. S of E will also become this previous one plus the union of the rest, which will be A, B, C, D, E, F. And so will be the S of A, S of D, S of F, S of C. All of them will be updated to A, B, C, D, E, F.
Yes.
Okay.
Yes, sir.
Yeah. I mean, that is fine. This is how you want what you want to do. But question is that by doing so, can you do it in linear time? That is not very obvious. Okay.
Sir.
So your job is that at any point of time, for every vertex, you want to keep a tag on or a set of all the vertices that are connected, that are in the connected component of that vertex. That is SU. Okay.
Yes, sir.
And then you have to keep on updating that accordingly.
So basically, at every step, we'll be adding one edge, right? That's what this SU and SV does.
What do you mean?
One edge, one vertex.
That's
one word.
What do you mean? SU and SV does? Yeah.
No. Like, sorry. Like, yeah, using SU and SV, that is when we add edges to A. Like when, like
there is a selected edge. Select that edge.
Yeah, when the set is not the same.
When the sets are not same. When they are from two different connected components. When the two vertices are from two different connected components, that means the two connected components, the set of edges, set of vertices in the connected component of U is not same as set of vertices in the connected component of V. I will add that edge in V.
Yeah.
Okay.
Sir.
S of U, always think of it as for every V or every U, S of U is at that time the set of all connected components of a set of vertices in the connected component of U. And S of V is set of all vertices in the connected component of V. Okay, now if these two sets are not same, then I know that if I add that edge, I am still fine. I don't produce a cycle. And I add that edge. But whatever is written here is slightly wrong. You should update all the SU and SV accordingly. Okay, for all the U and V for all X in SU in union SV, you want to update them to be SU union SV.
Yeah.
So that is what you have to do.
Right. But doesn't that already happen here in this particular step?
Think about it. Think about it. You will understand.
Sir?
Yeah.
sets, it won't it increase the time complexity?
It will increase the time complexity. So
Yeah.
that's why you need to use the data structure over here.
Yeah. So one more question, like
Union find algorithm.
Sorry?
Union find algorithm.
Exactly. Union find will do that. Good. So whoever knows union find will kind of be able to understand.
so one more question.
Yeah.
Like this is a greedy algorithm, right? Like
Right.
can you give me a greedy algorithm which doesn't give a correct output? Like it's not necessary, right? Greedy algorithms produces correct output.
Oh yeah, a lot of times greedy algorithms don't give correct answer. Lot of times greedy algorithm doesn't give correct answer. I mean, for example, depending on how you are defining the greedy algorithm, right?
Yeah.
I mean, what happens if I have just chosen that, okay, I will look at all the, I will look at all, say, sorry, here, I will say that, okay, what I will do is that I will look at all the vertices and look at all the edges going out. Whichever vertex, look at the degree, sum of the degree. Whoever degree is smallest, I will take all the edges from there. Right, that's a greedy algorithm.
Okay.
Okay. A simple thing is that, you can think of that, okay, like you want to connect the set of, you have to connect all the cities using fiber network, okay? A simple thing is that, okay, take a vertex city and connect, you would like to connect all the neighboring cities from that city. Take a vertex with a maximum degree and connect all of them.
Yeah, like minimum vertex cover, are you looking at something?
That's a greedy algorithm, right? And they will not give you that. Correct. So greedy algorithms are, it's very easy to come up with greedy algorithms which doesn't. Minimum shortest path is a typical example, right?
Yeah, like what makes this problem, like, and this algorithm gives us a correct output, like even though we are choosing some sort of greedy algorithm.
Say again, there are many times, so there are many greedy algorithms, okay?
Yeah.
No definition of this is a good greedy algorithm or bad greedy algorithm. There are many greedy algorithms, okay? And there are many greedy algorithms, and many of them give you very good output. You're proving it is can become complicated, and the many greedy algorithms that don't give very good output. So maybe if you guys are interested, what I can do is that maybe in the next class, I will then move to another greedy algorithm. I will not be doing about this MST. Instead, there is another algorithm on MST that I can present. But otherwise, I can go into another greedy algorithm, which is used in machine learning a lot, called the perceptron learning algorithm. I will present it in the next class. And greedy algorithm that was that people that was being used, and we had no idea why that algorithm works. But at the end of the day, it so turned out that after 30 years, it was proved that this algorithm actually works. It took 30 years to kind of prove it. So greedy algorithms are very interesting set of algorithms, no doubt. Many algorithms don't work, and while some of the algorithms work. So it's hard to classify that which kind of greedy algorithm will work or which kind of greedy algorithm will not work. That is not easy to classify.
Okay, sir.
Okay. Yeah. So let me see next class what I do. I might do this another algorithm. You might have heard of it, the Prim's algorithm for minimum spanning tree, or we can explain you the machine learning algorithm. But that will require some amount of linear algebra. But we will see to that.
Yes, okay, sir. Machine learning.
Sorry?
The machine learning, the perceptron algorithm.
The perceptron algorithm? Okay, I will, yeah. Yeah, let me think about it. I will possibly give you the perceptron. Okay, I think I have to drop the class now.
Yeah, thank you, sir.
Yeah. So I will see you on Thursday. So